Hello. In this video, I'm going to show how to solve this problem involving two charges, a positive and negative charge, and a conducting circle in the middle. So basically, we're told to draw the field lines and the equipotential surfaces. Okay, so a couple of things to note when you're drawing the field lines and equipotential surfaces for a configuration including a conductor is that a conductor, well, being a conductor, conducts electrons. So if there was a voltage across the conductor, the electrons in the conductor would move to equal out that voltage, and they would continue to move until those voltages are equal. So all points along the conductor have to have the same voltage. If they didn't, electrons would move. Okay, so well, all points along the conductor have the same voltage, aka the same potential. Also, the field lines are always perpendicular to the edge of the conductor, because if they weren't, they were coming in an angle that would push the electrons in the edge of the conductor. So the potential of the circle is constant, and the field lines much approach it. So from the perspective of field lines going from the positive charge to the negative charge, we can kind of imagine that the white background has some material with very low conductivity, maybe like water or something. And you can think of charge flowing from the plus to the minus. What it would do is it would come out of the plus, and rather than like do this big long journey through the water, it would cheat. It would go a little direction, hop into the metal, and then zing around the other side, and then go across. That would be a much more efficient way to get from positive to negative. So as a result, you see the field lines, they go like this, and then they have to come in pointing. They have to come in pointing perpendicular to the edge of the metal. And then they would pop off over here. We see them coming into the negative, out of the positive. It's possible you could have a few field lines that go all the way around from the positive to the negative without hitting the conductor at all. Probably won't fit in this picture, though. Note that I do not draw field lines within the conductor. Every point on the conductor is 0, therefore every point inside of it is also 0. There's nothing to cause a field inside. Okay, so that's that. Now let's draw some equipotential surfaces. So I'm going to draw those in blue. So you notice that when I draw it like this, the equipotential surface is perpendicular to all of the field lines, as it should be. Also note that the equipotential lines do not go through the circle. Because the circle has the same potential, it's like in the analogy to altitude, where you're drawing equipotential lines as topo lines, like on a topo map. The circle is like a circular field, perfectly flat circular field. In that case, well, if it's a perfectly flat circular field, it'll have no topo lines going through it. If you look on a topo map and you see a big part of the topo map that has no lines, that means it's flat. Okay, so that's what that looks like. You'll get a few of these circles going around the peaks, aka the charges, and then I'll have something like so. So that is more or less how you draw the equal potential surfaces, field lines, E. Okay. And that is that. You could draw them more densely, but I think this gets the point across.